Hi, today we're going to look at a voltage follower. I'm going to start with a simulation, and then we're going to look at it in a sort of live display. I'm going to start off by just reminding you of some of the characteristics of an ideal operational amplifier, and they are that it has an extremely high input impedance, so no current flows into either of the inputs. An operational amplifier has massive open loop gain, so when we don't put any feedback from the output to the input, the operational amplifier will have a gain in excess of 100,000 or more. The operational amplifier has a high input impedance and a low output impedance, and the two inputs, the non-inverting input and the inverting input, they form something called a differential amplifier, which means any differences between both of the inputs is amplified by the amplifier, and when the signal is the same on both inputs, the signal is not amplified by the amplifier. This also leads into something known as common mode rejection. Simply that when both signals are the same on both inputs, no amplification takes place, and that's quite an important property for some circuits. So what I'm going to do first, we're going to show the follower, and what happens with a follower is we take the output and we simply connect it back to the input like this, and then we're going to do the simulation. We've got an oscilloscope here, and I'm going to run the sim, and I've split apart both the output and input, but you can see that they're an exact mirror copy of each other, and I'll move them together like that. And the reason no amplification takes place is that when the output is fed back to the inverting input, as I mentioned earlier, there's no difference between the signal on both inputs. So all we get at the output is an exact copy of the input. The major benefits of an operational amplifier follower are that we have an extremely high input impedance, over 1 megohm usually, because the signal goes into the non-inverting input. We have a low output impedance, and just as importantly, we have high bandwidth and we have a stable amplifier. So those are the four major benefits. When we open loop gain the amplifier by grounding the non-inverting input, you're going to see, as I do the simulation, that the output swings massively positive. And it goes so high, in fact, that it goes above the limit of the power supply and just flattens off. That's what you see when we go above the headroom of the power supply. So there you are. That's the operational amplifier as a follower, and I'm just going to take you on to a practical demonstration of that now so you can see it in action live. Okay. Okay, so here we've got a situation. What I've actually done, if you're looking at the scope, if I ground the inverting input, the output swings massively positive and negative. It's swinging so far, in actual fact, that it's distorting. It's hitting the headroom of our amplifier. What that goes to show is the massive gain of an operational amplifier, and that's obviously cured by employing negative feedback. So as soon as I connect the output back to the inverting input, like so, we see that the negative feedback brings the follower's output to a gain of 1. The chief benefit of a voltage follower, apart from the high input impedance and low output impedance and the employing of negative feedback, is that we greatly increase the bandwidth of the amplifier, and we also make it much more stable when we employ negative feedback.